Fusion is one way in which you can contribute to making clean, abundant energy. And if you imagine this big superconducting thing kept at cryogenic conditions with that tons of weight and doing that, that's a thing that most smart people would look at and say, I'm going to go for a coffee and maybe you won't see me again. But in January, we incorporated the company. In February, we signed the term sheet. In April, we moved the team from all over Germany, from MIT and from Google X in California. And we're all in Munich. So Munich is the right place because that's where the ecosystem is.
Welcome to Tough Tech Today with Meyen and Miller. This is the premier show featuring trailblazers who are building technologies today to solve tomorrow's toughest challenges.
Welcome to Tough Tech Today. Forrest and I today are joined by Francesco Sciortino, who is the CEO and one of the co-founders of Proxima Fusion. Now, this is our first episode of our fusion theme, one of the parts of the future of energy. And so, Francesco, welcome. Could you tell us and get us all involved in the world of fusion? What broadly is this source of energy, and why is this really important for us?
Happy to do that. Thanks for the invitation, first of all. So fusion is we like to say, the ultimate source of energy. It's the only energy that has not been really fundamentally harnessed by humanity. It's the way the stars are burning, fundamentally. So most of the energy that we indirectly use, you could say, really comes from, in some way, from fusion. The reason why we haven't really been able to directly harness this is because it's very hard. So the reason why we're after fusion for so many decades is because it could be clean, it does not involve CO2, it does not involve large amounts of radioactive waste. It has a lot of benefits. We're hoping to also make it economically viable. Fundamentally, to have this technology entering really widespread use for humanity, you have to make it commercially viable. That's one of the steps that we're still working on. There are many different ways of trying to do fusion, and I think the jury is still out there to determine which one actually reaches that market fit.
So what would you say is the biggest challenge to harnessing fusion, other than it's basically like having the sun burning, I guess, somewhere on Earth? Or is that an appropriate description of it?
Yeah, I think saying that we're trying to build a star on Earth is definitely appropriate. Depending on which fusion reactor concept you're thinking about, it could vary what it looks like. It definitely looks very differently than an efficient power plant. So some of the key differences, let's say, are that fission involves heavy nuclei, and we split the heavy nuclei and we transform part of the mass into energy. In fusion, we still fundamentally use Einstein's formula E=mc², but we're trying to join nuclei, hence the name fusion. And we try to join very light nuclei, usually forms of hydrogen. So the concept that we at Proxima Fusion focus on involves magnetic confinement. So these kind of devices, we are focusing on stellarators, so a subclass of the magnetic confinement fusion concepts. These stellarators look like donuts, but they're very twisty in some way. So they look like big magnetic bottles where we try to confine high energy matter that we call a plasma. Different groups around the world are trying also to make fusion with laser systems. Some others try to use big pistons. There are all sorts of varieties, which make for a very entertaining moment in the history of fusion where, different groups are really going out with very different ideas. I would argue that the magnetic confinement fusion is the general concept that has the highest technology readiness level. It has been researched the most for specifically the purpose of energy. So this is a very demilitarized field that has positives and negatives, I suppose. We don't get funded by defense money, but we really have always had our eyes as a field on making energy. And the reason why Proxima Fusion exists is because obviously we think we have a shot at making this economically viable, as I mentioned earlier.
Is there something at the point in fusion work, particularly within stellarators, a competitive aspect? Is this kind of like not to draw on the military aspect, but like we've seen, or know the story of Oppenheimer. There was a rush between sort of the Allies and Axis powers to be able to figure out this new form of energy and how to harness and direct it in certain ways. Do you feel that there is that this is different with fusion, that it's a different kind of approach and maybe collaborative rather than competitive?
Whether there is a breakthrough, you mean? So whether there is something that has really been changing the game? So in the case of fission, there was an interest in accelerating for military reasons, but actually even before, it was the ability to slow down neutrons and to understand how fission reactions actually happen. I think now everyone knows the story thanks to the nice Oppenheimer movie. In fusion, there have been a number of important milestones that have happened over the last few years, and some of these relate, let's say, to different fusion concepts. Many people have heard of what the National Ignition Facility has achieved finally in December last year. It was the first time that a laser system produced a gain factor of energy production of more than one. And this, one has to be careful about how you phrase this. It's energy it's a statement about the comparison of energy that is absorbed by the plasma and energy that is released by fusion. And it's very different than a comparison of energy at the plug and energy produced and going back to the plug. But this was certainly an important milestone on the laser fusion side, which then allows us now to actually do scientific exploration of the conditions that were achieved in those experiments. At the same time, in the world of magnetic confinement fusion, there has been a lot of effort in advancing the technology, and there have been a lot of interesting devices that have been brought online. From the perspective of Proxima, we're based in Munich. We're the first spin-out company in the history of the Max Planck, and we are born from the observation that there is a device that we look at as the most visionary, amazing example of what we can do as humanity in terms of tough tech, and that device is called Wendelstein 7X, or W7X. And we look at this machine and we think there isn't just... Describing these as breakthroughs wouldn't be quite correct. There are lots of milestones. And a lot of people may find that the distinction between milestones and breakthroughs to be, we always want the breakthroughs. But actually there is something very nice when you rise on the path of technology readiness levels, or TRLs for short. It's the milestones is what you want. You want to keep the breakthroughs in the physics lab, and you want to know that you understand what you're developing, and that ideally, you're really not doing so much pure research on a more basic level, but you're actually doing the technology expansion. So W7X, when we look at it, we see lots of things that look like a power plant. In 2015, speaking of milestones, 2015, the device turned on. 2018, it crashed every record on the planet for stellarators. So W7X is by far the most advanced stellarator on the planet. By 2021 or so, the device was running in continuous operation. Last year, it was run for 8 minutes at high performance. These are really milestones that show that we can move forward. And the physics involved here is very similar to the one of tokamaks. So we work on stellarators, but the other, maybe even more the more conventional magnetic confinement fusion concept is called the tokamak. And a lot of the physics is shared here. So some of the milestones that have been achieved on tokamaks over the years really apply here. So from an experimental perspective, there are all these construction of devices. We've learned the most by building stuff. This, I think, will resonate a lot with tough tech people. You want to fundamentally build. You want to, you learn a lot by doing cool design, and you want to have put all the AI fuzz that you can in your story, but fundamentally you have to build it to actually know and iterate in the most effective way. And the W7X to us, it's the most relevant, very large scale demonstration. It's a prototype about it's the relevant timescale for a power plant. It shows a lot of what we need: steady state operation with high magnetic field, superconducting magnets, but it's not built to make energy.
What's the specific differences between a stellarator and a tokamak?
So a tokamak, both of them look like donuts in some way, and both of them have big magnets. And these magnets everyone agrees now they have to be superconducting so that they can run in steady state for long times with not so many losses. And then there are some so-called high-temperature superconductors that now allow us to go to even higher fields. The key difference between the tokamaks and the stellarators is in, you could say, the symmetry. So the tokamaks look the same as you walk around the donut, and that's allowed by the combination of large magnets and a solenoid. So a system that if you imagine the tokamak like an apple, it's the core of the apple, and that core of the apple is inducing a current. It's acting like a transformer, really, and it's inducing a large current through the plasma in the long direction. The presence of that large current is what allows you to combine currents and external magnetic fields. So you end up with a spiral of magnetic field. This is, if you just see a picture, if you just Google it quickly, you get the picture. It's not terribly complicated. It's a smart idea to try to have these helically winding magnetic field lines without having coils on the outside that follow the field lines to some extent, that are all curvilinear in some way. So the stellarator instead is the other option, where you do not intentionally create a current through the plasma. Instead, you do everything with external coils. So you don't have the transformer in the center. And if you look up what W7X looks like, which is now, by definition, the modern stellarator, then you'll see these coils that are all twisty. And depending on what kind of engineer, physicist you are, you may look at W7X and think, oh my God, this is the most horrendous thing that anyone ever built. Or you think, this is really fantastic. It's incredible that we've ever managed to build this. So W7X is the definition, let's say, of this concept these days of a stellarator with modular coils. The critical difference from the tokamak is there is no externally imposed big current.
It looks very cybernetic or organic, like it almost looks like the coils and the material around it are almost like randomly oriented. Is it like very precise, the kind of construction and placement of these coils, or why does it look so like, almost like random? It's not, cleanly divided into.
Yeah. So it has symmetry, which may not be apparent at first. But a machine like W7X has a 5-fold symmetry. Actually, you could cut it in 10 equal parts, so arguably 10-fold symmetry. But when you look at it closed up, you see all this cryostat, and you see lots of more than 100 ports, so points of access, and it looks just like evil in some way. The stellarator, as of today, the so-called, you could call it modern stellarator or optimized stellarator, is really, it requires computation. Stellarator really entered a completely new age when supercomputing became available. In fact, in the late 90s, late 80s, early 90s, the Max Planck Society in Germany had the first supercomputers, wanted to show some muscle power, and so decided, it had all the skill sets on the theoretical side, on the computational side, and started working on optimizing stellarators. And that's how W7AS came about. That was the stellarator before W7X. That was very successful. It had a relatively small number of things that needed to really be checked and investigated. It could have run for much longer, I'm sure. But then there was the opportunity to go the next step. And as I said earlier, building these devices gives you way more learning than anything else you could do. So Germany was able to fund and build in the north, in a town called Greifswald, the new device, W7X, which was much larger. And there, the computational power really was focused on the shape of the coils. And here I connect to your question. So the coils may look like they're randomly shaped, but actually that's where a significant chunk of the computation goes. And there are old ways of doing that. There are newer ways of doing it. The way we're working on that in Proxima makes the most, let's say, of the fact that it has been 2 decades since we actually optimized W7X. So one thing is to design the coils and the system around it such that you reproduce physics of the magnetic confinement that you think represents the performance that you want to achieve. The next thing is actually building it. it may look like you design a thing, then you send it off to some big company and they're just going to deliver the perfect thing for you. And that's a nice dream. Unfortunately, I think most people that have tried that at some point have gone through some pain. The experience with W7X was extreme, though, in that respect. The reason why it's, the cost, this visionary project required more than €1 billion or $1 billion, give or take, of funding, of public funding. And one of the key challenges in building this was that the coils, imagine these twisty coils, had to be placed in some sort of oblique position, and they had to be placed and manufactured and placed with 1.5 millimeter tolerances. And if you imagine this big superconducting thing kept at cryogenic conditions with that tons of weight and doing that, that's a thing that most smart people would look at and say, I'm going to go for a coffee and maybe you won't see me again. But for some historical and rather very interesting, there is a lot of really fun history behind why this project actually kept going. There was a similar project in the US that instead was cancelled because the tolerances were so extreme and industry couldn't produce these parts. Instead, W7X actually kept going until 2015 when it was turned on. So there are really a lot of details, a lot of know-how that has been developed in Germany and Europe in general on how to design these machines, and then actually how to build it. And the industry that has built those parts is what's behind the Proxima story and why we think we can go faster than if we were just an isolated group of nice, friendly folks,
Yeah, it's really interesting and the exciting how Proxima is the only spin-out from the Max Planck Institute, and that as they think about it, the ecosystem, sort of economical manufacturing, et cetera, that's around within the region and within Europe and Germany in particular, is set up to perhaps be the right place to be able to actually physically make this complex thing. Yet your background academically, I understand you're a co-founder and you have Imperial College London, the Swiss Institute of Technology, MIT as well. Could you walk us through a bit about that background story of what's helped lead you, around back to Munich as, this is the right place to make this?
Yeah, sure. So my background, I started out in physics. I finished my high school in England. Originally, I'm from Italy, as my name makes very clear. And then I studied physics and got into plasma physics with an interest in the extreme, let's put it that way. So there was a really fun experiment in the underground of Imperial College, which is in the center of London. And every once in a while, you could feel the ground shaking because there was a Z pinch. So a device that creates columns of plasma at extreme conditions. I thought that was too fun. My supervisor back then was a really great guy. And then that's how I got started. It was more with an interest in astrophysics plasmas. But then I had a chance to go to EPFL, this Swiss Technology Institute. Great place. There is a tokamak. So one of these more conventional magnetic confinement devices. An extremely good machine for science investigation. This is called the TCV tokamak. And there I got the fusion bug. And I guess I didn't get too distracted after that from fusion. And I think what unites me with my co-founders is the fact that we came from engineering or physics backgrounds and we were looking for a way to try the hardest ultimate solution. So we're some sort of group of radical people that are, we fully embrace that there are lots of important things to be done for decarbonization, for moving society in the right directions that we can discuss at length. Fusion, it's not the quick one. If you want to have an impact in society within the next year, you should go for something else. As a physicist or as an engineer with many different kinds of backgrounds of engineering are needed here, fusion is one way in which you can contribute to making clean, abundant energy. And that was the bug that I could just not get rid of. So then I stepped through Princeton at some point, and then I did my PhD in fusion at MIT. I worked on the tokamak on the MIT campus called Alcatraz CMOD, and then on the D3D tokamak, which is the General Atomics in California. And during this time, while I was working on Tokamaks, I had already seen that there was something. It's not too hard to. It's easy to notice that tokamaks have some issues with losses of confinement. These so-called disruptions, they happen in devices that have large currents, like tokamaks do, and these are not something that I think can really be solved. Let's say you can mitigate them, but you can't really solve them. So when I went to Germany, I joined the only organization on the planet that has both a large tokamak and a large stellarator. The large tokamak is called Aztec's Upgrade, and it's in Munich. And the large stellarator, of course, is W7X, which is in the north of Germany. So I moved to Munich as a city that is developing as the new deep tech capital of Europe. And there, the Max Planck was going through this phase of starting to consider what's the future of the Institute for Plasma Physics. After Aztec's Upgrade, I got involved as a European coordinator for scientific research in one of the most promising ways of thinking about tokamaks, so-called negative triangularity plasmas, which I had also been doing some research on at D3D in California. And as I kept drilling into the topics of negative triangularity and tokamaks, I started looking for something different. And I think the transition to believe that stellarators are the next step, really I owe it entirely to my co-founding team. So those that then became my co-founders, many of them were in Greifswald, where W7X is located. They have been working on Jorrit Leon, one of my co-founders. He had been doing research on stellarator power plants and the technology and physics trade-offs that you get when you think about the full system at scale. This was very inspiring to actually to talk to somebody that was not doing scientific work only, but that was looking at the trade-offs as we see them actually impacting the energy production system. So Jorrit was an important influence, let's say, in that respect. Talking to Jonathan Schilling, another one of my co-founders from W7X, was really impressive. The moment he starts talking about W7X with all the bits and pieces, it gets you excited very easily. And then other team members, Andrea Merlo, and there have been multiple pieces of the story. Jim Felix Lobsen started telling me about how you can now design the coils of W7X with much greater tolerances. So we have the design capabilities today to actually build a device like that at much lower cost, taking the single biggest cost drivers and reducing them drastically. And these were really the kind of things that make you think, okay, so the problem with stellarators historically, they have been that they were really hard to build, but we built a really, really great one. This could be done in Germany with the industry that has really pushed the limits of what is possible. We had problems historically with stellarators not confining the fusion products, the fast particles, the helium particles that are produced by the fusion reactions. I'm using all synonyms for the same things. And then in 2022, publications came out, the first one by Landerman and Poe, that showed that actually we can do it. We can now optimize stellarators numerically to confine these particles. Then there was the question of cost, which, as I said, the biggest cost driver is the construction of big coils. We think we have that under control. It's not easy, but we have a path forward to make it easy. So all these, issues started coming down, and we started seeing that there is a commercial case to be made. And then we started talking to people in the outside world, something that we don't do quite enough in public research maybe, and it was really, really helpful, it turns out. So we started understanding that the path is long. The one to have, thinking about a fusion power plant is not a thing that you want to do with a time limit of a couple of years. You need the right kind of investors. And we started talking to the right people, and we decided that it was worth doing. So then in January, we incorporated the company. In February, we signed the term sheet. In April, we moved the team from all over Germany, from MIT and from Google X in California, and we're all in Munich. So Munich is the right place because that's where the ecosystem is. There are lots of good things to be said about startups in Boston or in California, but the ecosystem that is key to stellarators in particular, this is where Germany has invested a lot more and has made the right bets. And sometimes you make bets, sometimes you lose them, sometimes you win them. And so we are here because a good bet was made.
Amazing.
Could you walk us through a bit about what the conversations are seeking investment, justifying what this look like potentially incredibly expensive, long time horizon, kind of like sort of a capital intensive project, and how it's being positioned as not just a project but as a business. Could you articulate kind of how you set up that storyline and the organization to make it happen?
Yeah.
Because I think that's something that's really challenging within the tough tech community is being able to
Yeah.
kind of nail that right.
Yeah, so I think should be clear to everyone that what we're doing is at the extreme of the extreme in terms of the materials, but also the business side. So we're talking about having a first of a kind power plant within the 2030s. That's big enough to say there is a big uncertainty, and we think it's feasible within, before the 31st of December 2039. We think there is a real chance of doing it earlier, but the truth is that we have to make a lot of progress to define how much faster we can go. We do think that by 2031, we can build a stellarator in Munich that would demonstrate everything that it takes to make net energy. So that's one date that we see as sticking to. In between these two big milestones, one needs to focus on the intermediate milestones. And the intermediate milestones for a stellarator, of course, to some extent relate to the coils. So that's where a significant chunk of our work goes. Here, the story of high-temperature superconductors is central to all the magnetic confinement fusion companies. So a big one from spin out of MIT is Commonwealth Fusion Systems. They have now raised more than $2 billion to build the tokamak, which is being built in Devens. The team there is great, and I think they have been pushing the field as a whole forward with a tokamak, which, as I said, I see some significant challenges with. But the technology of the magnets, great stuff. Tokamak Energy in the UK has also been pushing for quite some time on high temperature superconductors, or for short, HTS. And like them, the question is, can you show continuous progress? Can you demonstrate to investors that you're building intellectual property along the way? In our case, which we are very much in the mindset of not getting distracted by trying to access side markets. So we are not aiming to sell software or pieces of machines. We're aiming to sell power plants, big stellarators. And clearly this is a business that does not, it's unlikely that there will be 100 companies doing that some 20 years from now. It's likely that there won't be just one fusion company. There is no reason to think that there would be just one player that survives the fusion competition, let's say. So when you look for investors, you have to, in this domain, I think, one needs to get some numbers right. The capital needs are large, so is the size of the market. The energy market is humongous. The moment we started going fundraising and some investors were asking us, what's the size of your market? The answer there is, it's big. It's bigger than you care. I mean, just if you manage to deliver these products, then we bring humanity into the next phase of its civilization. So let's talk instead about milestones. And some investors will want to know, okay, how do I make sure that I can track these milestones? And how do we make sure that you grow in the very best of ways? And that's where our focus is on at the moment. So the path is long, but if you keep it if you focus on quality of execution and you can, still get it within the lifetime of the funds of the investors, those are all important things.
Mm-hmm. So I like how you've really cast it, in terms of milestones rather than projecting it as one day, something magic will happen and then fusion will just appear. I think that's a good lesson to learn for kind of all tough tech entrepreneurs, is you really do have to look forward to kind of that what seems like a breakthrough at the end of the tunnel, but build out all of the milestones to get there and make progress incrementally on those. And that's how all probably most big breakthroughs happen.
Yeah, so.
And then kind of to the public, they appear like it's, voila, right? But
yeah, this happens all over the place, right? In AI, there have also been a lot of there has been expression of great surprise for ChatGPT and so on, whereas the milestones that really brought us to all of generative AI, for example, they're clear to those that actually look into the topic. Same for fusion.
How do you decompose a project of this complexity and this technical uncertainty into meaningful milestones? Because I'm thinking maybe there are analogs in biotechnology or like med devices even where there can sometimes be 10 years from invention to when it's actually like helping the human, and being able to have the kind of vision of what this thing could be. In this case, the like a fusion reactor that's going to be powering everything, and then figuring out how to split that apart or sort of devolve it all the way back to the present day. And what do I then, as co-founder of Proxima Fusion, need to work on tomorrow to start down that pathway?
I think every company tries to do that in different ways. Of course, it's dependent on the specific technology. The one approach would be to try to think of what can you commercialize first. So let's say you make a company that works on tokamaks and you're making big magnets. You may want to sell magnets if you can. So on your way to fusion, you try to identify the pieces of the story that have the highest TRL and you try to commercialize those. That's one approach. We're a little more radical. So instead, we are prioritizing first having...
Because that's kind of like Commonwealth fusion systems,
yes,
right?
I mean, tokamak energy. And this is a very reasonable way of doing things. Of course, it's smart, even, I would say. But it's smart, and it could be complemented. Let's put it as a hypothetical. It could be complemented by a different approach, which is to focus on the concept that gets you to the full product. So if you're really focused on a fusion power plant, then you would really want to know that the pieces that you're working on along your way are actually relevant to the final thing. So that you don't just build more things, you actually try to take the quickest path to the final product, which here is a very sizable big reactor. So what we are doing is we are focusing on this design of the power plant. We're not working on the intermediate device, which we do think we will need. We're working on the first of a kind power plant. And then we're going backwards. We're thinking, okay, what are the pieces that you need? So the magnets are clearly a really big one. So everyone agrees on that. The magnets, the moment you show me a magnet of the kind that we need, which is non-planar, high temperature superconducting, hey, hands up, that's a big milestone for sure. But there is a lot more to that. You have to actually be able to support the forces. So how it's not that the bigger the magnet, the better it is. At some point, you need to think about putting this magnet within an ecosystem of structural support, and then you need to have space for the shielding of the neutrons, and you need to be able to breed tritium, which is a form of heavy hydrogen that we need in these devices. And then you want to think about TRLs, I think. And in our way of looking at things, TRLs are really, I think actually this is the lesson that the NASA, the commercialization of space in the US especially has transferred to some extent. That is, think about things in TRLs. So we are looking at TRLs, the lower ones, for example, related to tritium breeding. Those we're trying to create partnerships with academic partners. And what concerns physics, we try to also do with academic partners. Here we come back to why being in Germany, why being within an ecosystem with the Max Planck Society, with the Karlsruhe Institute of Technology, the Research Center Jülich, these three big organizations that made the history of fusion. And those are the ones that we think can help us on the academic side to lift those very, the lower TRLs. In terms of instead the higher ones, you want to avoid getting lost. I fully feel your question. This is such a big device. Where do you actually begin? It really helps if you've done it before, doesn't it? Sounds too simple to say, but if you have a prototype that you've put together before, that really helps. So, of course, I didn't build W7X. I'm in awe at the people that actually did. But as Proxima, we are lucky to have those people that advise us, that help us. Lutz Wegener, earlier today, I was lucky. I feel always lucky to be able to pick up the phone and talk to Lutz Wegener, who was head of assembly of W7X for 20 years. Lutz has an incredible amount of know-how, which is not in patents. It's not in some papers. It's in his head. And Lutz is interested in transferring this for the next stage of the story of stellarators. So is Felix Schauer, who was head of cryogenics and then head of internal components on W7X. These people are those that help you to say, okay, I screwed that up last time. It costed us a lot of time, a lot of money. Step by step. Take project management seriously. It's not a thing for those that don't want. Project management should be technical project management. It's not management of people. It involves people, but the efforts that we're making now is on looking at the history of how things have been done on W7X, focusing on there are some things that are clear that we have to focus on. As I said, the magnets, the performance of the magnetic confinement, but then think about how you develop things based on experience. Mm-hmm. That the industrial partners also really help. Yeah.
You kind of pricked my interest on some of the other challenges as I'm trying to create a vision of what this is in my own head. So you definitely made it really clear that the magnetic confinement is a huge challenge. And of course, managing the different forces. I'm kind of curious, when I think of a power plant, I think of, some sort of fuel going in, something coming out, and energy. Can you kind of dive a little deeper into what is the fuel, what goes into it, what comes out of it, that sort of basic level understanding?
Yes, so on a fundamental level, you need to create a plasma, which must be confined by this magnetic field created by superconducting coil. The fuel there in a power plant, we expect to be deuterium and tritium, so the two heavy isotopes of hydrogen. You insert them, you add them into the machine. So the machine at first is vacuum. It's a very large volume, so creating a vacuum in such a large volume is actually fairly challenging. You puff in some gas of deuterium, some gas of tritium, and then you have to define how do you ionize them and how do you heat them to 100 million degrees, 150 million degrees. Here, different companies try different things. Here is one place where we disagree even among people that within the field there are different opinions, let's say. And there are forms of microwaves that you can use that resonate with the ions or with the electrons. Some people really want to push on particle accelerators called neutral beam injections. That's the technique. Some of these things have each has a different challenge. Let's put it that way. Once you manage to heat, to ionize, and then heat this gas, so it once it goes above a few thousand degrees, it ionizes, and then it starts following the magnetic field lines. Once you create high enough density, high enough temperature, and you get good enough quality of confinement, meaning that the particles stay there for long enough, then you start getting fusion reactions. There is a finite probability of the deuterium and tritium having a strong enough collision that then produces helium and a neutron. The neutron will fly out because it's not electrically charged, so it's not confined by the magnetic field. The helium instead is ionized, and therefore it's part of the plasma. And somehow you need to get that helium out. But first you want it to share its large energy with the deuterium and tritium particles in the plasma. Let's leave the helium there for a second. Looking at the neutron, that's the energy that you want to harvest. So that neutron must go through whatever initial boundary you have. Happy to chat about that challenging boundary. And then you want that neutron to be absorbed. You want it to heat something, and you want that heat to be transferred to a water system, which fundamentally then creates vapor, and that vapor you want it to push a turbine, and the turbine you want to go into a very boring, very old-fashioned system, which we are not innovating on at all. So the focus is on how do you produce that heat source. There is another part that happens when the neutron goes outside of the magnetic confinement, which is to breed tritium. So while I mentioned we are using as fuel deuterium and tritium, the deuterium is easily available. You find it in water, so the ocean is full of deuterium. It's cheap, easy stuff. The tritium is a lot more complicated. At the moment, the initial source of tritium that we have comes from fission reactors, the heavy water boiling reactors. There is the CANDUs in Canada are the main source in the world, and those, we have enough tritium to get quite a few machines started in the new commercialization of fusion. So the problem is not so much the startup, but you cannot rely on the CANDUs making enough tritium forever. You need to breed the tritium inside the fusion machine. And how to breed this tritium, in practice, we all end up talking about lithium. So you need to have enough lithium such that when the neutrons collide with some lithium composite of some sort, the lithium breaks apart and you get some tritium. You need to be able to extract that tritium and push it back into the machine. And you need to make more tritium. There will be some engineering efficiency to this process. You need to make more tritium than you consumed, so that you always have some leftover. You always need some margin. So if we manage to do that with this system that we call the blanket because it surrounds the plasma like a blanket does on a bed, then we should be self-sufficient in terms of tritium. And so the things that you're really consuming are deuterium and lithium. And then you need to have the heating, the power to get the machine started. But the fusion dream is that you are in a situation where you make so much fusion energy that you can turn off your heating systems on the outside, and the plasma just keeps heating itself just by fusion. So you keep getting the neutrons out, but the helium keeps heating the plasma itself, and you end up with a machine that just keeps transforming mass into energy. That's what we call ignition in a magnetic confinement fusion concept. It's not a theoretical concept. This must be possible. We've never seen it. We've seen fusion. We do fusion on many devices on the planet. We just haven't made an economically viable amount of fusion. And going into ignition is not necessary to make it economically viable. But wouldn't it be nice if we managed to build an engineering system that manages to keep these extreme conditions? The materials must survive these conditions, not for a nanosecond. They must survive it for hours, because that's what the market fit demands of us. So keeping that coherence of the concept, I go back to an earlier point. We're focusing on that coherent concept in Proxima, trying to identify what are the critical things that we may want to forget about today, but really they're going to bite us back in a few years. So we're attacking those as much as possible early on. That's why we talk on our website of a simulation-first approach. So we think we have the tools to design the solutions to a lot of problems, much better than a tokamak can. So the stellarator is this computationally enabled concept where we can get this done. On a tokamak, we don't think so.
Amazing.
Are there things like control rods in place that we would have like in fission to prevent runaway conditions? Because I'm kind of picturing, as you're talking about, so like breeding the tritium, I might date myself, but like there's an I Love Lucy episode from TV that where she has like a special piece of yeast or something, and the bread loaf basically just keeps growing out of the oven. Is there like, we're gonna have like so much tritium and we can't stop it? Like, do we need to put these reactors underground, or
it would be
up in space where we have a vacuum built in?
It would be really amazing if we had too much tritium. I think that's unlikely to be our problem in the near future, but generally there is no safety. These machines are inherently safe. In fact, the problem with fusion, unlike fission, is that it's too hard. So fission, you take two uranium rods, you enrich them, and you put them next to each other, and the two things, they want to make fission. There is no analogy really that is easy in fusion. You have to take these gases. You have to put the gas there in the first place. If you don't add fuel, there is nothing to burn fundamentally. And then you have to heat this thing in extreme purity. You have to put it into a vacuum system at first, keep that purity up, and then heat it to 150 degrees. If I manage to take off my shoe and throw it in the vacuum vessel, that would turn it off. That's it. This thing has to stay extremely pure. The density of it is very low. So as soon as there is an impurity, it's done. So it's the opposite problem of fission. You don't have an equivalent to the uranium rods. Also in terms of waste, this is also an interesting thing to consider. So you don't have radioactive waste that is being produced as part of the production cycle. the machine itself, we're talking about the most energy dense source of energy in the universe. So yes, the machine is extremely under stress, right? So the machine the internal surface will become radioactive. That means that this should not be talked of as anything easy. That's a significant challenge, but you don't have the uranium rods coming out. That's pretty nice.
So it sounds like fusion is more like the early days of computing, where actual insects were computer bugs that would mess up the whole system, and now with fusion, it's any sort of unexpected thing that shows up in the plasma area could make the whole machine shut down in a safe way.
If you had a bug inside the vacuum vessel, the thing would not turn on, unfortunately. So we're worrying about very minuscule imperfections in our setup. I wish the bug were really the limit.
Wow.
Yeah, it's very hard to get it going. But once you do, if you have a system that works, we look at the stellarator as being particularly interesting because it's intrinsically a steady state concept. You can keep making power indefinitely. There is no pulsed anything anywhere in the story. Yeah? So it's really like a microwave oven. You can turn it on, it just stays on, there's no surprise, and you turn it off when you want. That we can come back to is what we think is needed for the market. You need to be able to design a thing that has this level of stability. You need to get to these extremely pure conditions, these extremely high temperatures, and then you need to stay there. And so we are very attracted to something that does not have any form of pulse, any transient, because those are the things that fundamentally I think work very well in a research lab and not so well in a production facility where you're pushing on all the material limits, where you find out when you make a bigger device, extra problems come up. So we're looking for something that is very predictable.
I had a question about alternative fuels, mostly for my personal interest. My company works on mining the surface of the moon.
That's very nice.
Also a far out sort of 2030s timeline.
We want to talk to you, I think. If you guys...
Yeah, one of the things on the moon, is
of course
helium-3. Yeah. Is that of interest in this type of reactor?
For sure. If you get us enough helium-3, we'll be happy to consider doing deuterium helium-3, which there are a few companies that think that is the first kind of fuel that we should work on. Now, nobody, as far as I know, is counting on your wonderful company getting us enough helium-3 in the near term. But in the long term, I think we should pay attention. Now, even in the long term, though, there is a fact which we have to always consider, which is that the reaction rate between deuterium and helium-3 for fusion is way lower than the deuterium-tritium reaction. So the benefit of doing deuterium helium-3 is that it does not involve neutrons. And neutrons are nasty. Neutrons are, challenging because they smash materials, they displace atoms, they make things radioactive, all of that. But, in theory, if you have a system that can manage those energies on materials and you can harness the neutrons, it's okay. But it's a significant part of the challenge, dealing with neutrons. If you have a fuel, deuterium and helium-3, that does not make neutrons, but just transforms mass into thermal energy, let's put it that way, and you can harness that, just the heat, there could be easier ways of doing this. So Helion is very well known as a company based in Seattle, and they talk about deuterium helium-3. They think they can make the helium-3 by deuterium reactions, and then they have a very efficient fuel cycle that keeps the helium-3 in the loop, and they accumulate helium-3, and they think that they can make that is enough. I think that's very difficult, let's put it that way. So I don't place my bets on this. Also, even if you manage to do that, as I said, the reaction rate is much lower. So there you go, you have a difficult problem. You just made it harder. Of course, you made it easier in terms of the neutron challenges. So it's a trade-off. Obviously, what I think is the most promising path is clear, I think.
Awesome. Well, if you change your mind and you need to put in an order for helium-3,
I'll be right at your doorstep. Yes.
We'll go try to scoop some up.
Please definitely bring us some, because it would be, it's on the horizon. If you imagine fusion in the long distance, yeah, sure, it could be, deuterium helium-3 would be very interesting. The thing that we are working on, the way in which we phrase what are we trying to do with Proxima Fusion is we work on the clearest and most robust way to get to fusion energy. So we are not saying that 1,000 years from now we're going to make fusion with stellarator, QI stellarators, so this category of stellarators that we think are the way forward. We're saying that's the fastest way to get it done. So if you take out all the idealization, all the I wish this was that, I hope this works out, we think you end up with a QI stellarator with DT.
Awesome.
Francesco, we caught you at a time when you're pretty in Austria. What's taking you away from the home base of Munich?
It's quite close. It's 2 hours away. There are some beautiful mountains here, and it's a great place to practice German, it turns out. And I recommend everyone to come by Salzburg. Salzburg is one of the most beautiful places on the planet, I think. Yeah, but I've been traveling quite a lot. Munich is the home base. Last week I was traveling between Berlin, Munich, north of Italy, and then been going to England. As I mentioned earlier, I'm gonna come by Boston and then LA, San Francisco. So I travel quite a bit. Austria is one of the places where you see the nicest mountains, and I love coming by here every once in a while.
Certainly make a trip down to Denver sometime and say hi. We'll show you the mountains around.
If I am that lucky, I will let you know.
Remember to come to the little Pennsylvania mountains too when you get there. One of the oldest.
Right, the Pennsylvania mountains are good. So check out JMill's homestead.
Oldest mountain ranges on the planet, the Appalachians.
Yeah.
That and the Urals.
I've come to love them while I was in Boston. I had some great times in New Hampshire. Mm-hmm. Was the go-to place for me.
Oh yes. It's sometimes it takes the unbuilt environment to help sort of clear the mind while thinking about some of the frontiers of physics and very deep engineering problems, practicalities of like trying to get helium and tritium.
Yeah. I don't expect to find answers in the mountains.
Well, maybe find yourself. That helps. The goal, I guess.
Yeah.
So what's with my understanding, at least 7 million euros in the bank that as part of a pre-seed round for Proxima. What's ahead for you and Proxima, and what are the particular resources, people, things that you need or are looking for, as you look ahead in the practicalities of building an insanely challenging but potentially world-changing fusion company? So
the creation of this coherent design of a stellarator power plant, this is a significant part of our current work. In the coherent design, in any design of a stellarator, you come up with, the magnets are really important, it turns out, and you'd better not be surprised when you learn that. So working on the magnets is a significant part of our work as well. We're doing that together with the industrial partners that worked on W7X before. That's another part. As I mentioned earlier, it's not the case that the bigger the magnets, the better. At some point, you have to create support structures, and it's a lot less trivial than it seems. You hit the limits of what steel of any sort can do. So then another big milestone is coming up with that design of the support structures. There we're using topological optimization to find structures that try to minimize the amount of material and still let us go to the highest field that is reasonable, let's say. And then there are aspects of the conceptual design that we're trying to also work on with our academic partners on the lowest TRLs related to the absorption of the neutrons. And then there is the work on materials and the heat exhaust. And many of these projects are collaborative. We see ourselves as the engineering company in the German fusion ecosystem that helps everyone to move forward, to make the most of this incredible advantage that we have in here thanks to W7X. And so we are, this ecosystem has to move in parallel, because we don't have the benefit of doing things in series. And these different projects now are being supported. We're looking towards a future where public-private partnerships are really funded as a way to go faster. And these are all things that we are doing now. The signs are very promising. You might have heard that the Ministry of Research of Germany has announced a 1 billion euro, give or take $1 billion of funding over the next 5 years for fusion. A big chunk of that is for public-private partnerships. Last week, the government of Bavaria, the state where Munich is, has announced interest in making a Bavarian fusion cluster. This is analogous as a concept to what has been done in the UK. Very good program in the UK that I think has taught us in continental Europe what a national program could look like in fusion if you take this really seriously. And now I think Germany has really woken up, and this has become now our attempt at making this a European champion. We're in Germany because here is where the initial investment, because that's where stellarators can really be brought to the next stage. But we see ourselves as a European company and tackling all of these different parts and looking for the right kind of talent. So you asked, who are you looking for? We're looking for the best engineers on the planet. Right now, we've been hiring from, Tesla and Google and an uncomfortable number of American companies, I must say. And then mostly we've been looking for people that can hit the ground running, but more junior profiles are also very useful if the people are really that quick, that smart. And we've been lucky to find some amazing people. And the path is of course, to build a stellarator, you need a whole lot more than a few tens of people. And so we are on an accelerated growth path, and we'll see where we get.
Fantastic. So if anyone listening to the podcast is one of those people that wants to join you or maybe has an interest in a partnership, how do they reach out to you?
I think LinkedIn could be a good way. If you see that there is one of the job adverts of Proxima on the proximafusion.com website, we'd love to hear from you through that. Otherwise, reach out to me via LinkedIn. I do read messages. We need people with such diverse expertise. It's amazing once you realize how much goes into a system like a stellarator. You go from the cryogenic stuff to the magnets to electrical engineering, mechanical engineering, and really everyone has a pretty tough job. That's the fascinating part. We need some of the best engineers and physicists on the planet for many different tasks. So if you're excited about the mission, if you think that this clicks with you, the general approach, then we'd love to hear from you.
That's really great. Francesco, thank you so much for joining us and kicking off our focus on fusion. It's a dizzying topic, but I really like how you have articulated and sort of given us that wherewithal, and what Proxima is doing sounds fantastic. I mean, let's hope our cities are powered by Proxima reactors. I guess in the late 2030s.
Won't be tomorrow.
Okay. Yeah. Okay. Good. Got it. Forrest, we need that helium-3 dump really
please.
fast.
Yeah, I'm working on it. So I'm getting a lot of fusion energy on my face right now. The sun just rose.
This was part 1 of a 3-part theme about fusion energy. Our next episode will feature a venture investor who has supported a different approach to stellarators, and I think you're going to really value her perspective on this. Also, hey, big shout out to Erica. Thank you so much, Erica, for becoming our first Tough Tech Today advocate member. It means a whole lot to me and Forrest to have you join us as we focus on the trailblazers who are solving our world's biggest challenges. Again, thank you. And now, parting words from our guest.
My name is Francesco Sciortino. I'm a co-founder and the CEO of Proxima Fusion, and I wish everyone to stay tough.